So this is my analysis on simulating the Massachusetts COVID-19 number of infections. So as a way of outline, I'll first define my variables, and then I'll show how to obtain my optimal alpha and beta. Then using the data we've collected so far, I'll do some analysis to obtain these optimal values of alpha and beta. Then I'll use these optimal values to do some simulations. So I define alpha to be my average duration of recovery. So if alpha is, let's say, 10, then the recovery rate is simply 1 over 10. And then beta is my infection rate. My ST, IT, RT have their usual meaning. Then I define N to be my population of the affected area. I'll show a modification of this quantity that accounts for the fact that not everyone in the population is kind of susceptible to the infection. So using Euler's approximation, I can then find an approximation to the change in the state of these parameters ST, IT, RT for any given time t. So using these three equations, equation 3, 4, 5, I will be able to simulate from my model once I obtain my optimal alpha and then beta. So to find the optimal value of beta, I decided to fix alpha since I don't know anything about the recovery rate. Then I optimize beta over this objective function where I take the fitted values for my infection and recovery and then subtract that from the cases at time t and then minimize this quantity. Once I minimize this quantity, I should obtain my optimal value of beta for a fixed value of alpha. As a way of analysis, I set n to be equal to 6.9 million divided by 50 plus 50,000. I assume that 2% of MA residents are susceptible to the infection, and then 50,000 have already been tested for the disease. So if I take 6.9 divided by 50 plus 50,000, I assume these are the people in MA that are kind of quite exposed to the infection at the moment. Then as a way of initial analysis, I fix alpha to be equal to 14. Then I assume my change in time point is simply 1, that is delta is equal to 1. Then I want to find my optimal value of beta. Just as a way of subjective judgment, I fix my initial infections to be equal to 5. So this is a graph of the cumulative number of infections observed from the data we've collected so far, and that looks at par with what we should expect. So as a way of initial analysis, so I fix my alpha to be equal to 14. I decide to optimize beta over the range of values from 0 to 3, and then the minimum sum of square deviation occurred at 1.4 million approximately, and the tentative beta optimal value there is 0.3061. Right. So I decided to use the obtain function in R to zero in on the exact value, and then using this obtain function, I realized that the exact value is actually 0.33. I also wanted to construct confidence interval for this value of beta, so I have to obtain the Hessian value, and this was given as the Hessian value. With this, I could obtain standard errors, and that allows me to construct this confidence interval for beta, 95% confidence interval, not 96, which is 0.32 to 0.347. So with this beta value of 0.33, I decided to see how my simulations will match up with my observations. So the red indicates the observed infection plus recovered for the MA, and then the blue line indicates the simulated values. It's matching the observed pretty well for the initial stages, but at higher levels appears to be some small deviations, but it's not doing that poorly. As a way of searching for as a way of trying to improve this model, I decided to search for over a grid of values. That is, I fixed various values of alpha and decided to look for the optimal betas at those points, right? So I fixed alpha to be 7, 11, 14, 17, and 21. And then my realization was that there isn't so much difference for each alpha beta combination. right? And that can be seen from the confidence interval I obtained for the beta values. So this is the upper confidence interval for the beta values, and the lower for the beta values. Their confidence weight is approximately the same. So I decided to do three simulations. The optimal case, where I have alpha to be equal to 14 and beta to be equal to 0.33. The extreme case, where we have a very slow recovery rate and approximately or relatively high infection rate. And then the favorable case, where we have a very fast recovery rate and then approximately high infection rate. Then if we check the optimal case, where alpha is 14 and then beta is 0.33, realize that at its peak the number of infections is just a little over 75,000. And then if we take the favorable case, at its peak the number of infections is just a little over 25,000. And if you check the extreme case, that is if the recovery rate is very, very low, they realize that at its peak the number of infections is roughly over 100,000 cases. That is the end of my analysis, and